This is the Earth Science Classroom. Welcome back to the channel. This video is in the Atmospheric Science playlist. It is one of the Atmospheric Science review videos, reviewing the material and content for the upcoming test. This video in particular is looking at GCMs, which stands for General Circulation Model, which is basically looking at how the whole Earth heats up in different areas and how that creates different circulation and convective cells in the troposphere to transport and move heat across the Earth from the equator towards the North and South Pole, and all the different winds and pressure belts and low and high pressure zones that are created because of this differential heating at the equator, and we're going to look at all the different processes that go along with that. So to look at GCMs and how the atmosphere moves as a large system, we've got to break it down into how this starts and how this initiates. Now, this is called differential heating. Differential heating is how certain areas of the Earth or locations are heated more than other areas. So this is a great example of how the Earth is tilted on the axial tilt inclination, which is 23.5 degrees currently. It does fluctuate, but we have this tilted Earth. This is the cause for the seasons in various latitudes, and the seasons get more pronounced and more diverse with the 4 seasons in the mid-latitudes compared to the more northern latitudes and southern latitudes towards North and South Pole, or towards the equator where the seasons are minimized, or there's only 1 or 2 seasons. So I have this red line showing the equator, which is 0 degrees latitude, and it's at a tilt, an angle, because of the actual tilt, and the Earth spins from west to east, and this gives us our 24-hour day and how the Earth rotates on its axis. So the sun, which is over here on the left, it gives us the solar constant, which is the general average amount of energy the sun puts out that we, the Earth, receive as a planetary system. The energy and EM spectrum and radiation, that is all coming at us, and we receive this energy, and the atmosphere receives it first, and then obviously the surface, both the oceans and land, receive it afterwards. And we do give off some energy, which we know is called albedo. But the energy we keep is what we look at, because the energy we keep in the atmospheric system and the Earth system, the oceans and land, that is what drives our GCMs, our general circulation models in the troposphere and how heat is moved. So around the equator, you have this very direct area that I'm marking out with black right here, that when the radiation hits this area, because the shape of the Earth is an oblate spheroid, it's a sphere, it's a bit fatter around the equator than it is from the north and south, as in up and down. So because this radiation arrives at the Earth in straight lines, the angle at which it hits the equator is close to 90 degrees, as in a right angle triangle. So therefore, the radiation, the energy from the sun, is hitting the equator or the equatorial region at a very direct and concentrated area. So the amount of energy, the solar constant that's hitting the equator is direct and concentrated, therefore it will become hot. Now the same energy that is traveling through space and hitting the north and the south pole at the same time is not having the same effect, because the shape of the Earth is a sphere. And you'll see that the area that the energy is hitting is angled. The energy is going to be spread out over a much larger area in the higher latitudes towards the North Pole, and the same spreading out of energy in the South Pole. That means that there will be less concentrated energy because it's spread out over this larger surface area compared to the equator. And the same thing up here, so it's less concentrated, and therefore it becomes colder because it's less thermal energy because it's being spread out, therefore it's colder. That's why generally the north and south poles are of a lower temperature than the equator. So what we have here, because of the sun's radiation coming in and received by the Earth in a straight line, and the Earth being curved, the surface being curved as the energy is hitting the Earth, it's going to distribute the energy and the heat, so it creates this differential heating, whereby the tropics and the equatorial region is warm and hot versus the polar regions, which is generally colder. Now the area in between, between 30 degrees north and 60 degrees north and south of the equator, this area is called the mid-latitudes. So generally there is a mixture of warm and cold air mixing in these locations, causing a lot of the variety of weather we see with mid-latitude cyclones, tornadoes, and hurricanes do start and originate in the tropics, but then make their way into the mid-lats to make landfall in certain areas. So the key is to remember that the equator is hot, the poles are cold because of the Earth's shape and because of the receiving radiation from the sun in straight lines or photons and it being concentrated through different surface areas. So the equator is concentrated and the poles is spread out. If we take a closer look at the equatorial region around the equator and we take our curved spherical Earth and make this section flat, so we can see this in a profile or a flat projection, as opposed to try and do it as a sphere. Now we have the equator right here, we have 30 degrees north and 30 degrees south, and in between we have the tropics, and we know this area is hot through the concentrated area and directness of solar energy and it being more consistent all through the year. So the sun's radiation comes down. So the absorption of energy happens here in the tropics through concentrated energy and direct angle and being consistent all year round. So you have this first stage of thermodynamics, which is our conduction. The air is going to touch the hot surface, be it ocean or land, and conduct the energy, the thermal energy, into the air. And we have this air that's going to start to rise. So you have the hot air through conduction, and it starts to rise up through hot air rising through density and buoyancy, and we have our hot air rising through different altitudes because the troposphere is between 12 to 15 kilometers, and this dashed line represents it, and the average temperature of the troposphere is looking at minus 60 degrees. So the pause is where the change in temperature behavior happens, and then the stratosphere begins. But we're looking at the troposphere, so this is the troposphere as our area to look at. So this rising air, this hot rising air, will increase in altitude, obviously due to pressure changes and a less pressure. As you increase in altitude, you're going to have a decrease in temperature, and that is caused by what's called adiabatic cooling, because there's no longer any more heat source up here. The heat source is down the surface with conduction. So as you go higher up, this air is going to progressively lose temperature and decrease in temperature as it goes higher up until it gets to a point of minus 60 at the pores. Now this air, being so cold, cannot sink right down because the hot air rising is too powerful and too consistent. So the air must go somewhere. Don't forget, this is a dynamic and fluid environment of gas moving all the time. So if we can't sink and go down towards the surface right over the equator, it's going to be moved north and south. So we move north and south. This colder air is going to be moved or pushed to the side, north and south, and it'll get to around 30 degrees or above this latitude, south and 30 degrees north, and it will be able to sink because it's far enough away from this rising air over the equator. So this cold air that is very dense is going to sink down over the latitude of 30 degrees north and south. So we have this sinking or descending air either side of the equator at 30 degrees north and south, and it's going to come down towards the surface and it's going to be pushed either side because the air cannot go through the ground, obviously being solid rock or ocean. Some might diffuse in the ocean, but majority can't go through, and it's then pushed either side, again, north and south. If it goes towards the equator, you get this surface wind being created to complete the cycle of moving air from hot to cold. So we have our beautiful convection of hot to cold, circulation of thermal energy, and this complete cycle we call the Hadley cell. And it is symmetrical, so it's the same on both sides, and we have this Hadley cell being formed through rising air over the equator and sinking air from the pores down over the 30 degrees north and south, and we can also link in our atmospheric pressure into this. We'll get into that later on. So if we expand this system, we have the initial catalyst or engine for our global circulation model, or a GCM, for the entire planet in the troposphere, you have the Hadley cell, two of them, symmetrical either side of the equator, being formed by convection cells for hot air rising and cold air sinking. Now it rises over the equator, which is 0 degrees, and it sinks over 30 degrees south and north, thus creating the first complete cell. Now I have drawn this arrow that is then leading off towards 60 south, and this arrow leading over towards 60 north. Now this is the initiation of a second cell that is next to the Hadley. So if we carry this on, we have the air that's going to move across the surface, the wind, and it's going to rise at 60 south. It's going to rise up again towards the pores, and again, same situation happens. Like the equator, it can't go any higher because it's too cold, and it's going to be moved, meet and collide and converge with this other part of the Hadley cell, and rather than going forward, because it can't go forward or higher, it has to go down, cold, and it's going to sink and rejoin, and this is called the Ferrel cell. That's next to the Hadley cell. So we can do the same thing over here on the northern hemisphere. The wind approaches 60 north, it's going to rise up. It's going to rise up towards the pores. It's going to split, and it's going to split over here in the southern hemisphere as well. And it's going to rejoin the Hadley cell here at 30 degrees north and sink because it's very cold. And we have our Ferrel cell over here. So we have our symmetrical cells forming because of air that's either being heated and rising, or it's cold with less heat and it's going to sink. And there's a final cell between 60 south and 60 north and 90 north and 90 south. And this is the polar cell. So we're going to have this situation where the air is going to sink again. It's very, very cold. And it's going to sink down towards or over 90 south. It's going to come back around across the surface as wind and rejoin at 60 and rise up. So we have a rise-in section right here over 60, and it's going to sink down. This very cold air is going to sink over 90 south, which is the South Pole, Antarctica, and the same thing's going to happen over here, the northern hemisphere. So it's going to sink down, very cold, over 90 north. It's going to sink, and it's going to hit the surface and be pushed back and rejoin at 60 north, which is going to rise up. And we have our polar cell in the northern hemisphere, polar cell in the southern hemisphere. So again, we have a symmetrical set of three cells, Hadley, Ferrel, polar. So the simple heating and cooling of air in the troposphere from the equator, because the equator is heated more than the poles, and you have this differential heating, you have these three symmetrical convective cells that form in the troposphere called the Hadley, which is around the equator, the Ferrel in the mid-latitudes, and the polar, obviously in the polar regions, that form to move heat, and that requires air. It's going to carry the heat in the form of wind, and wind can be across the surface or can be up by the pores. And you have this rising air and sinking air based on density, and whether it's being forced up or encouraged up with heat, to create these three cells over the Earth's surface. Now the reason why the pores is there, and it's kind of like a dividing area between troposphere and stratosphere, is because the cold air towards the pores is very, very cold, and cold air cannot rise. So that's like an unofficial boundary that's separating the troposphere from the stratosphere. I add in the surface winds and also the upper level winds. So these lateral arrows that represent the wind in between the cells that connect the rising air with the sinking air. And what happens is the difference in temperature will cause the air to rise or sink, which will then in turn cause the area to have either a low or a high pressure. Now the wind is air moving between pressure zones. Now the high pressure is going to move the air away, and the low pressure will drag or suck in the air towards it. So there is a balance between low and high pressure, which is causing air to move between the areas of pressure caused by temperature difference. And this wind is what we experience on the surface, which is like the trade winds or the easterlies or westerlies. So this will be in the next video, but this is the Hadley, Ferrel, and polar cell, which is our GCM, which is our general circulation model.